Binary search. Binary search is an efficient search algorithm used on sorted data sets. So the name binary itself means composed of two things. This is what binary means. So from here itself you can somehow conclude that this search technique divides the given array into two parts and then proceeds to find out the searched element in some manner. So this is the basic idea of binary search. Now, how exactly does it divide the array into two parts and how does it proceed with searching the element? That is what we are going to discuss in this particular lecture. So how does binary search work? It repeatedly divides the search space into two halves. So two halves will be almost equal halves. So it will divide it into two halves. Then it will eliminate one half. Let us say it eliminates this half. And it will decide that the search element, if it is present in this array, will be present in the other half. Then it proceeds with searching in the remaining half. Again, it does the same procedure. It will divide it into two halves and eliminate one among these two halves. So this is how binary search proceeds. So at every single step, it will eliminate half of whatever is remaining. That is how it is able to reach to the searched element much faster compared to linear search, because in linear search you are going through each element one by one. Here you are directly eliminating half of the array in each step. So this is how binary search is faster. So let us understand how exactly binary search works. We'll take an example, but keep in mind that this works only on sorted data sets. In case of linear search, you can have sorted or unsorted, but in case of binary search, the data set should be sorted. So let us say this is your input array. So your input array can have many elements, 12, 17. Keep in mind that this should be sorted, 25, 36, 44, 50, 66, 71. Let us say this is your array. So this is index 0, 1, 2, 3, 4, 5, 6 and 7. So how do you find an element that you want to search? So let us say you want to search for 44. You want to see whether 44 is present in this array or not. How will you proceed with binary search? The first thing, you have to find the middle element of this array. So the middle element of this array is, how do you find the middle element? You will do lower index plus the larger index by 2. So 0 plus 7 by 2 will give you 3.5. So you will take the integer part of it. So it will be 3. So you will go to index 3. This is what you have picked as middle element, your third index. What is the value in third index? It is 36. So the first thing you do is you will match the middle element with the target value. So you are searching for 44. You will search whether 44 is the middle element of this array. So in this case, it is not. If it is, then you can conclude the search there. You can say I already found 44 and 3 is the index. But in this case, index 3 is having 36, which means 44 is not present in index 3. So you have to either eliminate this part or this part. How do you identify this? You already know that the array is sorted, which means if this value you are searching for is larger than 36, it will be present in the right side of the array, right side of 36. If the element you are searching for is lesser than 36, then it will be present in the left side of 36. This you already know because your array is sorted. So whichever point you are at, you can simply easily understand whether you have to eliminate left part of the array or the right part of the array. So in this case, what is the situation? You are searching for 44 and you know 44 is larger than 36, which means the value 44, if present in this array, will be present in the right side of 36, which means you can eliminate the left part of 36. So this part of array, you know, the searched element won't be found there. So at present, you are only having this much of array in consideration. Again, you have to find the middle element. How do you find middle element? The index of first element plus the index of last element, 7 divided by 2. So what is 4 plus 7 divided by 2? You will get 5.5. You take the integer part of it, it will be 5. So you will go to fifth index. So this much is already eliminated. This is what you are having. This is what you are presently having. Here you will go to the fifth index. In the fifth index, the value is 50. So now you are looking at 50 and comparing it with 44. This time 44 is lesser than 50. So presently you have two options. One is on the left side of, because 44 doesn't match with 50, you either have to eliminate the right part of 50 or the left part of 50. How do you decide this? Again, you use the same logic. Is 44 lesser than 50 or greater than 50? So if it is greater than 50, you have to check in the right part of 50. And if it is lesser than 50, you have to check in the left part of 50. So in this case, 44 is lesser than 50. So you can eliminate right part of 50. Plus 50 is also eliminated. So here 36 also eliminated. So you went to the left part of 50. So in left part of 50, you are having only one element, which is at index 4. Again, what do? You check the middle element. And what is the way of finding middle element? First index plus last index by 2. Here you have only one index, which means first index and last index are the same. So you will do 4 plus 4 by 2, which will be 4. You found index is 4. So you search it. I'll take another color. You search it index 4. When you search it index 4, what do you find? At index 4, you will compare with the value 44. When you compare 44 with the value at index 4, you will see, yes, it is equal. That is, 44 is found at index 4. So you can return saying, I have found the value 44 at index 4. So this is how the search ends. So in case 44 is not present even in this index, then 44 is not present in this array at all. So just imagine if the value here instead of 44, it was 43 and you are searching for 44. So if it is 43 and it doesn't match, the value 44 is not present in the array at all because only one element is remaining and it's not there, which means the value is not present at all. So in binary search, you either reach this condition where you find it equal to the middle element, or you will hit the condition where you will complete the whole array and still the element won't be found. So this is how binary search works. So you understood what is the procedure in binary search. The next step is we should be able to convert this into pseudocode. Then only we'll be able to implement this. Now you know the logic. You should be able to implement this. In order to implement, first you should know how to convert this into a pseudocode. Okay. So what are the basic things we have to see in pseudocode? One, there should be a value low. There should be a value called high, which will see the lower index and the larger index, the initial part and the ending part of the remaining array. That is, initially you will be having from 0 to n. All the indices will be there in array. After you take middle element and you remove one part, then only the remaining part of the array is to be considered. So low will denote the lower index and high will denote the higher index of the remaining part. So this is one thing you want in your algorithm. You need these two variables. Then what do you need? You need a base condition. That is, in some condition you want to know, you want to identify that the target is not in the array. What will be that condition? Whenever the value low is lesser than or equal to the value high, there is at least one element remaining to be considered. Because if low is 0, high is 3, that means the array is having 4 elements, 0, 1, 2 and 3. If low is 0, high is also 0, that means array is still having one more element to be considered, which is index 0. Same if it is both are index 3, then index 3 is remaining. Only in case low is greater than high, that is, if your low is 4 and high is 3, that means there is no more element to be seen for. The complete array you have already verified. You have checked and the element is not found. So whenever the value low is greater than high, you can confidently say that the target is not in this array. So this is the base condition that you have. That is, if you want to say the target is not in the array, your low value should be above high at some point. So this is the base condition. So in order to write the solution, you should know this base condition, that is when to stop. And secondly, you should know how to divide the array. You have to have a mid value. Then you have to compare mid value with the target. And if the target is higher than mid, you have to only take the right part of mid element. If the target is less than mid, you should only take left part of mid element. So this is logically, it is clear for you. Let us write the pseudocode now. So how will you write the pseudocode? Let us say binary search of, you have an array and a target. You have an array and a target. So target is what you want to search for. That is the element you are searching for in the array. So first thing, you should initialize values of low and high. So you will have something called low, which is 0. And what will be your high? High also you have to initialize. You will initialize it as length of array minus 1. Why is it length of array minus 1? That is the last element, because indexing of array is from 0. So if the length is n, then last index will be n minus 1. That is why we are having length of array minus 1 as the high value, highest index. So once you define low and high, you can start a loop which will keep running. So in that loop, we'll have a while loop. While, what should be the condition? Low should be lesser than or equal to high. If low is larger than high, we'll come out of the loop. Whenever low is lesser than or equal to high, what should you do? You should first find the mid element. How do you find mid element? Mid element is low plus high. How did we find it? Low plus high divided by 2. So in order to indicate that this is integer division, I'll put 2 divided by here. So this indicates that it is an integer division. So if after dividing you get 3.5, you will only consider it as 3. So that is how you are going to do this division. Why is that? Because this mid should be a valid index. Your indices will be integers. So you found a mid value here. What is next? You should compare your target with this mid element. So you will compare if array of mid, that is the mid element, if that is equal to your target value, right? If it is equal to target, what will you do? You will just return mid index. So you will return mid. If it is equal to target, then you can return from there. If it is not equal to target, then what you have to do? You have to either go to the left part of mid element or the right part of mid element. How do you do that? If it is lesser than target. If array of mid, if this is lesser than the target value, then what do you do? So array of mid is lesser than the target value means target value is larger than the middle element. So you have to go to the right part. So in order to go to right part, what should you do? Initially your low value is here, high value is here. So if you want to go to the right part, you have to shift your low value to this point. So how do you do that? Your new low should be, what should it be? Mid plus 1. It should be next value of mid. So you should make it mid plus 1. So now your low is mid plus 1 means you're only considering right part of the array. And what condition is remaining? So this should be if else. So it should be if else. So because if this condition is met, it is already returning from there. So if both these conditions are not okay, what am I writing? It should be else if, no? So if it is else if, this should be the condition. If both these conditions are not satisfied, else, what should be the final condition? So one thing I'll do, I'll write an else if condition here so that you see exactly what is the condition. Otherwise, it should be just an else case. So if it is not equal to, if it is not lesser than, then only one thing is remaining, that is greater than. So what would be the condition here? AR of mid would be greater than the target value. If mid element is greater than target value, that means your target value is lesser than the mid element. So you have to go to the left part. If you have to go to the left part, low value should remain the same, but high value should be shifted from end to one step left towards mid. How will you shift that high value? You will do high is equal to mid minus 1, right? Mid minus 1. So this is how you will shift high value to one step to the left of mid. So now you have completed all the required steps. So if the element is found, it will be found inside this while loop. While this while loop is running, at some point you will find the element if it is actually present in the array. If it is not present in the array, it will come out of this while loop whenever low is greater than high. So in that case, what will you do? You will return minus 1. So minus 1, just it is an indicator that your search is unsuccessful. So after this complete while loop, if you are still not able to find the element, that means in your array, the searched element is not present. So that is indicated by returning minus 1 value whenever you are coming out of the while loop. So this is binary search algorithm. So the next step, whenever you write an algorithm, you should be able to understand the time complexity and space complexity of the algorithm. So how do you identify the time complexity and space complexity here? So space complexity is easy. Why is it easy? Because you just have to see for extra space. This algorithm, as you see, it's only defining two new variables, that is low and high. So that is order of one space at this point. Other than that, it is not using any space at all. Whatever is the given array, that is being used. Other than that, there is no space used at all. So space complexity of this algorithm is order of 1. So this is an iterative algorithm, that is why it is order of 1. If it is a recursive algorithm, it will take space for recursion stack. So that will be counted in space complexity. Here, as it is an iterative algorithm, space complexity is order of 1. Next thing is time complexity. How do you analyze the time complexity of this algorithm? In this algorithm, what is happening is you have an array. This array at every point is divided into half, which means initially if it is n, it will only have n by 2 size in the next step. It will only have n by 4 size in the second step, after the second step. So unlike linear search, in case of linear search, we had seen time complexity was order of n. But in that case, you were going through each element one by one. That is why you had to go through all n elements, and hence the time complexity was order of n. Here, because this is binary search, you are not going through each element. You are every time dividing the array into half. So whenever you keep dividing it into half, 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 and so on, and you boil down into one element, time complexity will be order of log n. So how is this coming? We'll see now. How exactly is this log n turning out? We'll see this now. But you should have this logic in your mind. We'll see it with mathematically, but you should by default have this logic in your mind that whenever you have a problem, any algorithm in which a given input is there, that is being divided into half, 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 and so on, and you boil down into one particular element in any way, whether it be in case of tree, array, or whatever, time complexity will be order of log n. That is, if you are dividing it as n by 2, again by 2, n by 4, again by 2, n by 8, and so on. If that is how the steps are decreasing, then it will be total of log n steps will be there. Then what is the time taken for each step is a different question. So let us see time complexity analysis exactly. We'll do this only for one problem so that you understand how it is log n. After this, when we go forward for other algorithms, we'll directly write it as order of log n. So here we'll exactly solve it down mathematically so that you get a logical understanding how it is log n. So let us see this. Our array size is totally n. N is the size of our array. And what happens after first division? After first step, what happens? This n will be n by 2 because half of the array is eliminated. So only n by 2 will be remaining. After second step, after second division, what happens? When you again divide array for the second time, this n by 2 is again divided into half. So the remaining array is of size n by 4. Similarly, if you do k divisions after the kth step, what will be the size of this array? It will be n by, what will it be? N by 2 power k. How is it n by 2 power k? After first step, it is n by 2, which is n by 2 power 1. After second step, it was n by 4, which is n by 2 power 2. Similarly, after k steps, it will be n by 2 power k. So this is how our division is going to reduce the size of array. After k steps, the size of array remaining will be n by 2 power k. Next thing is, till what point will you keep dividing the array? You will keep dividing till this value n by 2 power k, n by 2 power k is 1. Till the point this is 1, you will keep dividing the array, because whenever it is 1, only one element is remaining. You compare it and you will either find the element there or you will stop the search. So you will continue this search at max till the point where n by 2 power k is equal to 1. So if you find the element in between in any of these steps, you will stop it there. But in the worst case, you will go till the step where n by 2 power k is equal to 1. So whenever n by 2 power k is equal to 1, you know n is equal to 2 power k. Correct? So if n is equal to 2 power k, what is the value of k? K is log n to the base 2. So this is basic mathematics. That is, if n is equal to 2 power k, then k should be log n to the base 2. So if k is log n to the base 2, what does it mean? You at max, in the maximum case, you will have k steps. In binary search, in maximum case, you will be having k times you will be performing division of array and a search of mid element. So maximum is k times, which that k we know is log n to the base 2. So now we know that maximum number of steps we'll have in binary search is log n to the base 2. So this is the maximum number of steps we have. So in order to find time complexity, we want to find what is the time taken to execute each step and how many number of steps are there. So here we know there are totally log n to the base 2 steps. The next question is, in each step, how much time does it take? So in each step, what happens? You have an array. You simply pick middle element. So that is order of 1. Picking middle element is a constant operation, because you just have to find the middle index and you will directly get. So it is constant operation. Then you compare the given element with middle element. So that is also constant operation, order of 1. What is remaining? You will find whether it is larger, equal to or greater than, and then you will change the value of either lower index or the higher index depending on which part of array you want to eliminate. That is also a direct order of 1 operation. That is a constant operation. So you have log n steps and each steps take order of 1 time. Each step is constant. So the work done in each step is constant. So you have total log n steps. Each step you have to do constant time. Each step takes only constant time, which means total time is order of log n. Log n to the base 2. We generally simply write as log n. It is log n to the base 2 in this case, in case of binary search. So this is how time complexity of binary search is order of log n. So going forward, keep this in mind that whenever you see that in an algorithm, the value is n and it gets divided by 2, again divided by 2, divided by 2, and you keep on doing till it reaches 1. Then the time complexity, or you just remember that number of steps that it takes, that will be log n. So then total time complexity will depend on what is the time taken for each step as well. So that factor is also there. Here time for each step is order of 1. So total time is only order of log n. So this is how time complexity of binary search is order of log n.